Alright, making a video on draftphysics.com, debatephysics.com, video presentation. Keep trying, and I really don't understand why I am the only person that recognizes that there's, something needs to be fixed, that physics isn't quite right. And I can write this over and over again, but 25 times the fuel, okay, to go 5 times the velocity. So no matter what I start with, 10 miles an hour to 50 miles an hour, the argument is that I have to use 25 times the amount of fuel to go 50 that I use when I go 10. Gigantic. And you can reduce it to the more common one where they basically claim that something going 3 times the velocity, okay, equals 9 times the work. It's 9 times the energy. It's an equivalency. Work or energy. Come on. Do you really see that in real life anywhere? 9 times? Come on. And again, I pointed out, the only really good piece of experimental evidence we have of a nice clean experiment is the Mythbusters crashing the cars. 50 miles an hour, 100 miles an hour, car crushes twice as much, not 4 times as much. And they use clay and they get the same result. And they use springs, and the springs indicate the same thing. If you have a spring on both sides and they hit each other at 50 miles an hour, both springs compress the same amount they would compress if they hit a brick wall. Because yes, they're both going to stop, so to speak. But if you did a single spring, it would be obviously twice the compression of the spring. Twice the speed is twice the compression, twice the force. That's all. How do you defend this, this silly formula, and with this silly v squared? I mean, how do you defend it? Because it just doesn't happen in the real world. And I really shouldn't have to go over this over and over and over again. So anyway, you see, I watched some physics lectures. So I've been watching the ones from Yale. Shakar, Ram something or other, some Ram name. I don't remember it. But anyway, and they just talk right past the subject. In terms of not recognizing when they start talking about kinetic energy and momentum that they're not consistent, that they can't conserve both when they change the mass, and they just ignore the glaring fact that it just doesn't fit and it doesn't make sense. And then they talk about gravity, and they always do it in this the way Newton didn't write it, okay, F equals ma, when the a part is just a change in your velocity. It's not anything special, and it's not some new function. And even the idea that it's a constant force, it's only constant in units of time. So it's clearly time dependent, and the fact that I have to go over that over and again. And so I was thinking about, they were talking about what Newton would think, or what Newton, kind of like you listen to some Feynman crap, and Feynman talked a lot about, frankly, not just memorizing and not doing all that stuff and asking why, and these are obvious why questions that nobody wants to ask, and it just doesn't really make sense to me. So anyway, this idea of what Newton thought, and as I imagine it, they did think of originally, I think, quantity of motion as being something, a something that something possesses, and that something can exchange through contact. And I can't say for sure, but I'm going to make my argument that that's always how I thought of it. And the Newton's cradle gives you such a clear example. One ball goes in moving and it stops, and the other ball leaves moving. It seems clear that whatever this one possessed it gave it to the other one. You know, and that it's a something, not a nothing. Alright, so I guess I'll just stick with the title, which is something like force and matter. And I have the little force bits there. And obviously I could just make electrons and protons as circles, and those force bits. And I could just say, okay, you have these two kinds of objects. And I can tell you that, you know, mathematically this works really well. That if you imagine that every red bit every blue bit that hit a red came out red, okay? So it came in blue, or in this case black, and it left red, and that every red bit that hit a black thing, okay, came out black. You could understand that if that's the way it works and it doesn't get any momentum, you know, only when a red thing hits a red does it push it, stick to it. And only when a black thing hits a black does it push it or reject it in the sense of reflecting. But you could just understand that, okay, black is inert to red and red is inert to black, so you can understand that every bit of black force that comes from this side is going to be converted into red force here, okay, and every bit of red force that would have hit the other red object, right? This was all heading for this. It's not going to get there. It's going to be turned into black stuff. Okay, so it's not going to hit it. I mean, you'd understand that there's just no pressure between these two because the pressure can't get to them. So they're going to crash into each other. And if I reversed it, you know, in terms of putting an electron facing another electron, the exact opposite is going to happen. Every single bit of red force coming this way, all right, is going to be converted into black. And so that's going to happen on both sides. Every bit of the red, okay, every single one of them is going to be turned into a black. And so the blacks are going to be a ton of black force here, and every bit of black force is something that will stick, will push. It will stick to the object and push it. So you can understand why they would reject each other. So the protons are going to do the same thing as these electrons. And, you know, it's such a simple mechanism, and it creates, you know, Maxwellian charges. But, I mean, it's a key thing to understand that, you know, when there's electrons on the surface of atoms, you can understand that they're doing this all the time, you know, in terms of always radiating black. So no matter what color goes in, it radiates black, and this radiates black. So it never produces a red reflection, or red is always destroyed. And so the red things are radiating red, the black things are radiating black. And so you can understand that, yeah, when two electrons come near each other, they're going to have a repulsion to each other. They're going to reject each other, and they're going to push on each other, you could argue, with that force. The force is going to increase the pressure between them, and this is going to be a simple mechanism, like a spring even. You could just think of it as being elastic, and you're just pushing a force in. The force is going to compress the field between the two, and this one's going to feel the same pressure that this one was feeling, and you know, it's just going to transfer essentially the motion, and it works, and it's so simple. So it explains charge, you know, and it explains why dipoles are, you know, a special thing, you know, electron and a proton stuck together, the neutron. And it explains why at a distance the neutron looks neutral. Is because, you know, if I made it red and blue, you can understand from a distance it's going to look purple. Because the two are going to just mix with each other, and that's all I'm going to see. And I have to get close to it to see that, oh, it's got a red end and a black end and a blue end, and that's why, you know, I'm not going to see that unless I'm close enough to it. But there'd be the same thing as being neutral. Having one of each charge is the same thing as being neutral. So you can understand why, okay, you're going to call that a neutron, but it's really not a particle in and of itself. It's just the electron and proton doing what comes natural, which is sticking to each other. And the reason why they can't do it really easily, you know, the reason why they don't fly right into each other, is because this happens. You know, it's hard. They're in a field that's constantly pushing them, so they're doing this. This is their natural condition. If I just put an electron in space, this is its natural condition. And so the reason why it's a little hard to make neutrons is because they have to really, they're moving in 3 dimensions, by the way. So they're not doing just this, okay, or this. They're doing both of those. And so that's why it's not so easy to get them to line up, okay, and see each other, for the low pressure that's between them. They can't maintain that low pressure because they're always moving past each other and around each other. So it's only under the very high pressure inside of a sun where everything's getting pushed into each other, and so that's when they can get close enough where they can do this thing. And then as soon as you put them outside of that protected environment, outside of a nucleus, all of a sudden they're back in the noisy world, and 15 minutes later you have an electron and a proton again. No. Or you have a hydrogen atom, I would argue. But anyway, I haven't seen all the experiments they use to make any of those deductions, so it's hard for me to say exactly why they don't have neutron decay into hydrogen, because I would argue it seems the natural thing for it to decay into is a hydrogen atom, not an electron and a proton. And I think they're just saying electron and proton, instead of saying, well, yeah, it's a hydrogen atom plus an antineutrino. And the antineutrino is just mathematical rubbish. It's not a real thing. There's no real. That's pretty cool. Anyway, yeah. So yes, I'll turn that off eventually. I guess I should turn it off now, but I have to find my mouse to do it. So just arguing that people should appreciate that there are explanations, simple mechanics that can answer questions. You don't have to have a complex, crazy answer. You can have some very simple mechanism. So just by creating those 2 kinds of force, electron force, proton force, and having 2 kinds of matter, electrons and protons, I can create through 3 interactions, sticking, reflecting, and conversion. Goes in this way, comes out that way. Those 3 interactions, I can explain charge. I mean, something physics has just no. They don't say a thing. They just say it's pushing and pulling. They just say it's attracting and repelling. They don't say why or how it's doing any of it. So anyway, so I just wanted to make this argument just because in understanding motion and why it can even exist is just to understand that the matter, the electrons and protons, are dead. They don't have any go mechanism on their own. Their default is to just be stuck sitting there, and they have to have something motivating them, pushing them. So obviously what I'm basically arguing is that when a black force hits them, that's the only force that's going to be relevant for this conversation. We're just talking about electrons. It's either going the same direction, that is, it already has a Sisyphus pushing it, or it doesn't have one in the opposite direction or in this direction, and so then you can start moving it. And what it'll move is let's say the Sisyphus is going the speed of light, it might go 10%, okay. And if it has 2 Sisyphuses, it would be like 19%. It'll never be exactly twice. It'll be a little less, okay, because that's what prevents things from going the speed of light is technically the amount of pushing force isn't, it's a percentage, not a absolute amount. And but for our purposes in the big world, we know that we go much slower than the speed of light, a tiny percentage of it. So obviously the difference between 1% and 1.9% isn't going to be anything. There's not going to be a difference in terms of it's going to look like 2. So anyway, yeah, and so the simple argument is that your force, okay, is this stuff, okay, this stuff in the universe moving the speed of light. They're little bits of force, and the simple truth is it can stick, and then push the object with the understanding that you're taking a mass that might be 10. Let's say the force bit weighed 10 and the matter bit weighed 1,000. You can understand that now it's pushing 100 times more matter, and so it has to move 100 times less fast because it's 100 times more matter. So the tiny little bit of mass is added to this mass, and that's your new velocity, which is going to be, you know, a 1/100th of what it was before, because that's all it can add, pushing a boulder that size. So it either sticks and adds, or if it's already going, you know, if your electron's already got something pushing it in this direction, say it's got 2, and then you hit it in this direction, what's going to happen is both are going to reflect. That is, this one's going to reflect, and this one here is going to reflect. And so you're just restored this to having just one pusher. So it went from having 2 things pushing it to 1 thing pushing it. So that's the compensating force, so to speak. That's when you're, you know, providing an interaction, and you're going to exchange the condition, essentially. And then the third interaction is the one I described that has to do with electrons and protons. So these are only 2 interactions for electrons. The force either sticks or the force reflects, and there's a reflection this way. So you can understand when there's a reflection this way, that is when you have something coming against you, this force is still going that way. And this force is still going that way, except now it's going much faster. So this force is going much slower. Well, not technically, right? Because the forces leave at the speed of light. So I should have said that. The pushers, when they're free, they're always going the speed of light. And when they're stuck to a boulder, they can go all kinds of different speeds, depending on how many are pushing. So if you have a whole bunch of pushing, like a gamma ray, you know, a very high density of pushers, then this can get up to a very high speed. And that's essentially how we push electrons and accelerators, is you put a bunch of gamma ray energy essentially behind them and just keep adding more and more pushers and get the electrons up to a higher and higher speed. But once you get to a speed 3/4 or, you know, 90% of the speed of light, the amount of energy the amount of increase you gets smaller and smaller. So instead of getting a 10% increase, you're only going to get like a 0.10 increase in the velocity. So there's a point where you just can't gain much more velocity because you have to add so much more energy for any increase in the actual velocity. So that's why in accelerators this actually happens. You know, that it's very easy to get an electron up to almost the speed of light, and then you can keep adding energy, and instead of adding charge, you start adding heat. And so they change how they measure, okay, how many electrons are hitting, because they have to start measuring how much heat, because the electrons really aren't going to hit with any more velocity because they're already up to the speed of the force, and what you're really doing is just exchanging the force now. So you're just converting the force into heat rather into an increase in charge. But that's a subtle thing that I won't get into. But anyway, yeah, this simple diagram works really well. So again, I'm sitting here saying, okay, this I started with kind of a Sisyphus argument years ago, you know, where I kind of explained the force was like swimmers and they jump in your boat, you know. So, but yeah, it lacked a little bit of perfection in terms of, you know, the idea of the swimmer getting into the boat. Reflections weren't really, you know, very understandable, like they jump back in the water and start swimming the speed of light again. So it wasn't as good as, I think, this simple Sisyphus kind of argument, that you could just understand the Sisyphus as whatever, you know, little things that can go incredibly fast, okay, when they're free, and they're just the pushers. So that's the force, okay, and all the forces are made out of these, All right, and all you can do is change the pattern. So for electricity and magnetism, you're changing the pattern of the number of red bits versus black bits. Now electricity, I'd say, was mostly just black bits, and it's magnetism where you're adding the red bits to make a more complex pattern. And that's why only magnets can see magnetism, is because you have to have a dipole to see it. You have to have something that has an electron and a proton so it can see the red part and it can see the black part. Alright, anyway, I don't want to get into that because that's another complicated subject. And then, yeah, so all you have is electrons and protons. So you know the protons are safe inside the nucleus. Now there's there's electrons inside the nucleus too, I would argue. Now conventional physics doesn't say that, but I certainly do. And what you're simply doing is saying, if something's moving, Jesus. Yeah, well, I guess this pen has had it. If something's moving, it has to have something moving it. All right, and so that's the simple argument. So it's like the fluid argument you could add. You could say, yes, this quantity of motion is little bits that have a vector. So it's all Plancke, in the terms of these are elemental bits, and they all have the same mass and velocity. These are elemental stones. They all have the same size. And all you're really doing is just counting this force and calling it momentum when it's pushing matter. Now, it's also momentum when it's just Sisyphuses. All right, but we haven't defined the density or the size of those little bits. So they draw a photon. They don't tell you what's the substance of the photon. I mean, is it 3 little wavy things or 5 little wavy things? How long is the thing called a photon? And they don't do any of that stuff. And I can't do it for you right now. I mean, I think mathematically it's deducible, but I'm not a mathematician, so it's not going to get deduced tomorrow. By me anyway. Let's see, do I want to use this pen? It doesn't matter, I guess. It probably doesn't work either. Let's just see. It's okay. Alright, so what do I want to do in this video? I'm just saying it could be understood so simply that anytime two things are crashing into each other, all you're really saying is there's vectors they have a certain number of these Sisyphuses, and the simple truth is that they have to, through contact, what you're basically doing is pushing the electrons against the electrons, and so the electrons have Sisyphuses, okay, that are going to be between them, and that's sort of what's happening, right? Because you're basically saying, look, I'm going to turn the red things into black things, so I'm going to end up making Sisyphuses, so there's going to be an increase in the pressure, and that's all you really have to know, is that there's a bunch of radiating Sisyphuses coming off both of these things. So when they get near each other, their odds are they're going to take away any motion they have through that interaction. And you understand that it's going to be restored, okay, simply because of this fact that any energy, when the two electrons get close to each other, see, that's why I had to bring up the stupid proton force thing. It's just you have to have some explanation for where the pressure is regained from. Because the fact is you're going to reflect these little bits, right? As the electrons get close to each other, you can understand if they're moving this way to start, then everything will be reflections between them. And that as they start to move in this direction, then everything sticks, right? All the force bits that go, the blacks that hit this, will stick and stick and stick and stick. So they're not going to reflect back and forth again. There has to be opposing motion for them not to stick. And as they stick, their velocity increases, but you can understand the pressure is decreasing. And the only thing that's going to refeed that pressure is the fact that all the red bits are turning into black Sisyphuses. So you keep refueling the pressure between them until they get far enough away from each other, start moving fast enough that they're outrunning the Sisyphuses being produced by each other. They're starting to go fast enough that it doesn't matter that new Sisyphuses are being made, because they're moving away from each other so quickly, all right, that the speed of those Sisyphuses aren't going to catch up to push it anytime soon. I guess that's a way of saying it. I don't know if I'm that happy with that either. But it's, I'm just saying, if you think about everything that happens in that context, I have to do two kinds of erasing. You can make everything understandable in terms of how the energy, the force, is transferred between the objects and how to not transfer it. So I could make a simple argument that, because everybody keeps thinking these solid things have to move. So I have a big thing in space, it weighs 1,000 tons. Okay, and I'm going to hit it with something 1 ton. So it's 1,000 to 1 difference. Pounds, it doesn't matter what we use. And the principle is that this is going to be made out of a certain number of atoms. Okay, and every one of the atoms has electrons and protons in it. Okay, so you have a whole bunch of electrons and protons you have to move. Now what if, because the force is in discrete bits, that is, it's a number of Sisyphuses. Well, let's say I only have 5 atoms here, and say I only need 50 Sisyphuses to move those 5 atoms into this wall at 5 meters per second, something like that. Well, you could sort of understand that, I'm going to transfer these Sisyphuses. They're going to go from pushing this, when they're in contact here, the electrons are going to push on each other, right? So the electrons are moving. Yeah, the nucleus is moving too, so the nucleus is moving, which means the nucleus is pushing on the electrons also. So the whole mass of the atom, so you have to count all of the electrons and protons, because they all have to be pushed. The whole atom can't move unless all the pieces agree to move, so to speak. And they all move because they're communicating with each other with their force, the force they're radiating. So these electrons of this object are radiating their force. They're going to come in contact with electrons on the surface of this object and push on those electrons. So you can understand when they're compressing, creating an increase in the force, that all these electrons are going to start feeling it. But the fact is, you could understand that there's not going to be enough Sisyphuses to spread around. I can't take 50 and spread it over 5 million. So I can't take the literal force I have and actually put it into this object. All I can do is move the electrons. Because I can't move all the atoms, I can't move all the pieces, because all the pieces, there isn't enough Sisyphuses to push all the boulders. There's too many boulders. It can't push all of them, because it can't spread the Sisyphuses over all of them. It doesn't have enough. So the simple argument is the only thing that travels here are the electrons. The electrons all move, and then they move out on this surface. But they can't move out, because they're elastic. They're kind of stuck by this, attraction force. And so the whole thing, just kind of like a rubber band, the energy goes out on this surface. It doesn't have anywhere to go. The electrons don't have enough energy to leave, so they basically just push back in again, and the force just goes back the other way. And if the object is still in contact, well, now the pressure went across and came back again, and it's just going to push, the object back out and reflect. So this thing won't move. All it will do is vibrate. Now, if this object loses contact before this oscillation gets back to this surface, well, then it'll just keep oscillating for theoretically a very, very long time in space. But it's in contact with a constant field. So, every time it pushes out, every time these electrons push out, they're going to compress the energy that's coming towards them. They're going to move into it. And so they're going to meet more energy than they would have if they sat back here in that moment of time. And so, in a sense, they're going to give their energy to the field. That is, they're going to create higher frequency photons that are going to leave the surface. So the oscillation will dampen, but it requires that it has to dampen by creating some sort of photonic heat So the biggest one we recognize as heat is infrared. But infrared isn't the only. They're all heat. All photons are heat. You're just arguing that, yes, the ones that are easiest for us to see are the infrared ones. But obviously, you know that a visible light photon is even more energy, technically. I mean, not technically, but in practical function. Okay, it's made out of all the same components that the infrared one is made out of, and it's even more compact, which makes it more capable of disrupting material substances. So we know it's heat, right? There's no point in saying it's not heat. And we know a gamma ray can make things hot, so we know it's hot. So they're all heat. So all the photons represent is some kind of heat, and the heat is just energy. So that's where you connect thermodynamics to all of these subjects, is because it's all just thermodynamics. You're all just saying the Sisyphus is heat. You can have heat that scatters. That is, you can have heat moving in all kinds of, you can have your little bits moving in all kinds of directions. Okay, and that's the useless kind of heat. Or you can have something move from here to there. Okay, and that's heat in one direction. So it's the same thing as heat. It's motion of electrons and protons, and that's all heat is. Except heat, as we usually describe it, is, going in all kinds of directions. It doesn't have one direction. If you give the heat one direction, then essentially, it's an object moving. So you can almost see that in atmosphere, where heat can move through the atmosphere, and it's almost like a substance moving, sort of, kind of, mostly. Let's see, we have one comment. Imagine having Gary as a science teacher. I would have actually paid attention as a kid. Well, I would have appreciated, science that like I said, they drew that silly photon, and for me that was the end of having any respect for science teachers. I mean, for me, because it just didn't make any sense. And I guess I didn't pay attention when they were talking about kinetic energy, and my brain must have just shut down, because I certainly would have found it offensive even to be told that something going twice as fast is really going 4 times as fast, and something going 3 times as fast is somehow really going 9 times as fast. Because nothing in my experience indicated that was true. Now it's hard to think about gravity. I'm quite certain I never thought of it as a pull. So I never thought of it as being pulled into the earth, because I knew there wasn't a hole in the center of the earth where everything was being pulled. So I knew that didn't work, or that didn't make any sense. The rain analogy just always, I think, I can't say when I first thought of it that way, but it's just, to me, that's the intuition. So the stupid Valerie Rousseau guy, nobody's commented on his video, which I really do appreciate. It's basically conceding that nobody is thinking he's making a proof that he proved 1/2 mv squared somewhere, but he didn't prove anything at all. But the idea that you are collecting gravity, like you're collecting wind, or you're throwing something in a stream. I guess that analogy worked for me as a kid, is the idea that you're holding something and you can feel that it's heavy, because something is giving it weight, something is pushing on it, and now you have to compensate for that pushing force, just like holding something in water. As a kid, I used to stick my hand out the window a lot, and do that whole air thing, just from the speed of the car, and you would feel the pressure. And yes, the air is invisible and all that kind of stuff, and you're saying it's there though, right? So you could understand that, well, air can hit you, because it's material. But then you also know photons are heating your skin, so you really can't feel them pushing on you, but you can feel the sense that they're there and they're real. They're not like imaginary. Okay, they're a real thing that travels from the sun to me. It's not some kind of magical thing that's traveling from the sun to me, and it's bombarding and hitting. And so that kind of idea that it's a hitting force. So it is, like wind or like water or like sand or like, what else could we make it into? Little discrete bits. So any force that comes in discrete bits, you could argue, would behave exactly like gravity. So if we got rid of gravity and instead we had a big spray paint can out in space that was spraying paint, and the paint made you move, based on how much paint you got on you, it would make it all much more obvious, right? I mean, let's just say that we could see the pushing force because it would actually stick to you, and you could see it sticking to you. So you could see that when you're holding something, the paint is sticking to it, more paint. And then you'd have to have an analogy for the fact that, well, the paint that's on it is, ends up going into you and then into the ground. So that analogy sort of breaks. But you could certainly understand that. You could understand the time dependency thing, where going sideways, if I went sideways, that all that would matter is how fast I went across this, from here to here, right? If that's the only part that the spray paint is, the faster I go, the less paint's going to be on me, and that's perfectly consistent with how gravity works. So if I fly across a gravitational body very quickly, very little of the gravity affects me. I get bent very, very little, just like crossing a stream. So if this is a stream, just this video, and I go across the stream really fast, I don't go downstream much. But if I go really slow, I get pushed downstream. I mean, it's just so obvious that that's exactly what gravity's doing. It works the same way. It's the inverse square law. All those things work with that simple understanding of it's just stuff coming from all directions going that way. And then underneath me, there's stuff coming from all directions going this way. And the stuff below me has to go through the earth. And that's the catch. The stuff coming this way, a little tiny angle, it can still hit me. Okay, but those two equal each other. So that's not going to make me move. But, it's going to make me move a little bit up. It's a little vector going that way. But the fact is, everything underneath me, the earth, it has to go through some portion of the earth. And the average ends up being, the radius of the earth. And so it makes perfectly good sense that there's less getting to me going through the earth at this exact moment than there is hitting me raw. I mean, this is raw. It's open. There's nothing stopping the bits of force here. And you can understand there's obviously something in the way below me. It's a pinball machine below me. The ball just can't get to me because it's going to bang into a bunch of crap, move a bunch of crap, do a bunch of crap before it can get to me. And it's so obvious. And I'm just saying, 10 years? I've been doing this for 10 years? More than that. And nobody gets it? I'm just like, how can you not get it? How can you not understand that this works? Okay, and the only thing I got to explain is drag, and I have done that. But anyway, it's too good an answer to just say, oh no, we can't use that answer because it's too good. It works too well. It explains too much. The fact that the Earth is molten. I mean, what is the explanation? There's no other explanation than obviously there has to be an awful lot of energy that's being absorbed to make the Earth continually hot. And again, their theory is that the heat is 4 million years old or something. And that's so ridiculous because we can't make a perfect thermist. There's no way to make some kind of insulated chamber where the energy can't get out. It's not possible, because even if you create a vacuum layer, the photons are still going to eventually transfer the energy. It's still going to get cold. The heat will dissipate. And it's just amazing that I have to make these arguments. I mean, physicists should be able to understand that we can't make a perfect thermist. Can't be done. Especially one that's going to work for 4 billion years. It's ridiculous. Alright, anyway, let's see, more comments. I remember struggling with the concept of kinetic energy in physics because there were multiple instances where I used it to solve a problem and realized it gave me the wrong answer. Yeah, like I said, I didn't have the same experience. I only took high school physics, frankly, and I did, in fact, the physics, it was the only course they tried to fail me in high school. So, and I deliberately took high credit courses just to get out of high school early so I could go to work. So my senior year I only went to 3 classes, and I basically cut gym and English entirely. So I didn't even bother with the foreign language or something, one of them. I just cut, I said the hell with it, I'm not even going. It's just such bullshit. And so, I had whatever 183 cut slips, and anyway, so they were going to not graduate me, and I just said to the vice principal, go ahead, don't graduate me. You think I give a shit? It's just going to look bad on your records. Okay, doesn't bother me any. I've already got accepted at LSU. Why do I need you? What do I need you for? I don't need you. I don't need to show them that I graduated from high school. They've already accepted me. They already cashed my check. I never went, but I mean, it's just a fact. So, and what else I was going to say about that? Well, anyway. So, yes, and I was drinking and doing other things at the time also. I wasn't... I was starting to go crazy, essentially, and so school did not agree with me. But work wasn't any fun either. Anyway, they really weren't great years. So anyway, but yeah, that's the only physics class I took. But the funny part is I actually learned an awful lot in that class, and that was the ironic part. So the teacher he was a little bow tie kind of guy. We didn't get along at all. I was always, I was drawing hookahs on the desk. I was flirting with, I had a girl partner, and I was, I liked her, and, so we weren't really paying much attention. So the fact is he tried to fail me, and I went to the principal, and I basically said, you can't do that because I don't fit the definition of failure, because I did learn shit. And so, I forced him, he gave me an oral test in front of the vice principal, and I said, well, go ahead, give me an oral test. And I answered the questions right, and so he had to concede that I learned something, and so he had to concede I didn't fail. But anyway, so I got a D. But anyway, so that's the irony of it, though. I mean, it was a subject I was interested in. I just hated the teacher. But I do remember it, so that's the thing, I mean, I didn't do any of the labs. I didn't, I really did not pay much attention. But the concept of energy and motion was always interesting to me. So anytime you get to that part, I would pay attention. But it would have been so much better if he just showed the Mythbusters experiment and just said, look, see, twice the speed, twice the crushing, therefore there's no kinetic energy, so let's forget about this silly equation and just talk about momentum, because that's the only thing that runs the universe. Alright, well anyway, let me get back to the reading here. I remember struggling, okay, yeah, solved the problem, realized gave up the wrong answer. Okay, how can science believe the interaction in the small universe really operates as kinetic energy? Well, I just don't. So I'm just saying, when you break it down, you're just saying all you can do is move a mass, and you're moving a mass twice the speed. It's going to have twice the force impact on something. It can't have more than that. So you can only multiply it until, like I say, you start getting to these higher and higher speeds. Then all of a sudden the rules are going to change, because there's going to be You can have a huge change in something's velocity when you start moving it, but by the time it's going near the speed of light, you can't make almost any change at all to its velocity. And so that's where the rules change a little. And also the fact is now your Sisyphuses are moving almost the same speed they were when they're free. So you've kind of changed the equation. You've taken a little tiny bit of mass and put it on each Sisyphus's head in a way, and just eliminated the boulder altogether, and just said, oh, I've made some Sisyphuses that are a little bit heavier. But it's just really, you're converting all the energy is just the fact that you've got a bunch of Sisyphuses really in a small compact space. So you've increased the density of the Sisyphuses, which makes them very dangerous. Doesn't mean they have more energy than their absolute number, but the fact is when they interact with matter, they're going to interact with it in such a fast manner that the matter is not going to be able to react. Again, it's this whole argument that if I did make one of these objects that I say are, these are the objects that are inside of atoms. Okay, electron, proton, electron, proton. And you could really understand that this is the strong force in the sense there's no force required because what I described to you does this, right? It'll create this circumstance. The protons love electrons. They're going to get very close to an electron. And now the protons can't see each other. They can't see each other. They can't react to each other because they don't even know each other's existence. And so that's why they don't fly apart. It's because they can't see each other, can't feel each other. But if I knock this electron out quickly, you're going to understand before these attractive forces can react. That is, I knock it out quickly, then all of a sudden these two protons are really close to each other. All the black forces turn into red force. They're pushing on each other with an incredible amount of force, and they're going to gain a huge velocity. And that's the nature of radioactive decay and all that kind of crap, where you get this, this fact that you can create an awful lot of energy. Now, in some of the decay, what you're really doing is just pushing the whole electron. You're knocking a proton off and ends up pushing, you say you have another one over here, another electron. You're going to understand that you can create a mechanism now where the two electrons can't see each other and blah, 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 blah. But regardless, you're going to create a circumstance where these little bits are going to bang into each other and knock each other all over the place. All right, let's see. We just need really cutesy animations with pop culture references to get it. Well, I like animations, frankly, but I don't know about cutesy. Well, I think if you could get people to just listen to the simple argument that force is a something. It's not just magic. That force is something. It's a material something. And that, inconsistent with the Planck kind of idea, it's in quantized bits. That you could understand that, yes, if that force can stick to electrons and protons, that's all you really need is a mechanism transferring force into motion. And understanding that now all you can do is you can exchange that motion. See how to say that. You just migrate the Sisyphuses from one thing to another thing. You just exchange them. And that's what objects do when they collide elastically. And then if they collide inelastically, they end up releasing, something. Something has to be crushed and bent in terms of converting motion in a clear direction into lots of little motion. So you could almost argue that when you bend something, what you're really doing is changing the motion of the Sisyphuses, and now you're spreading them out. So they're not going in the same direction anymore. something like that. Yeah, I have to come up, I guess, with more players or some way to describe, because that is one of the interesting features, is how you convert motion this way into motion that way. And, you know, that was sort of in the Valerie's video. You know, it's just that idea is that, you know, if I have a stream, you know, and then I put something across the stream, you know, a ramp, you know, you really can't understand that now you're going to convert something that was moving this way, you know, into something that's going to be moving this way. But the price of doing that conversion is you're going to take a lot longer to get, for, you know, you're going to get here, okay, a lot later than you would have here if the ramp wasn't there, obviously. So there's going to be a lot more force being used because you're going to have to, you know, deal with the friction on this ramp. And so you're going to be putting pressure on it. And so there's lots of places where the extra time still means extra force, you know, because it's a time-dependent force. The stream is still hitting you. And so if you're taking a longer time to get somewhere, all of that extra energy has to be pushed into something. And so obviously the ramp is going to be collecting that. So whatever you've got it tied to at these two ends, that's going to be feeling the pressure of the thing moving in the water now hitting that surface, putting pressure on that surface, you know, causing heat and motion even. So it's yeah. So in that case, you don't get it for free. You know, it's not a free conversion. And it's not a free conversion in a lot of cases, you know, because you have to use, you know, car tracks have to use, you know, they slope the car track and then use gravity to help the car turn. So now the car doesn't have to use its energy to create friction because gravity's creating the force, keeping it on the track. And so it can go around the curve faster, okay, because there's nothing, it doesn't have to use its energy to create the turning force. The turning force is being provided by gravity. Yeah. Let's see what else. 4 viewers, not too good, but yeah. Is what it is. Let's see what else I could go over. Yeah, I don't know. I'm getting tired, I think. I'm just getting frustrated because there's just so much of this is just so obvious, and you're just saying, okay, I really shouldn't have to argue the time dependency of the force, and that's the part, I guess that's the one that's just really eating at me, is how these people can see me draw this stuff and then disagree and not be able to articulate how they're disagreeing. I mean, it's just so, it's so obvious how something falls in gravity, you know, that this is, if I take a time, you know, blah blah blah, it's this one, and the thing, all you need is this 1 3 thing, okay? You don't even have to do the 5 7 9. You could just take anything that falls a distance, okay? So no matter what distance it falls, no matter what it is, it's doing 1 3, okay? Every single time it's doing 1 3. Now it might be also doing, you know, I could cut it here as 1 and then do 3 5 7, but that's all you really need to know, is it's always doing 1 3. So no matter what the height is, 1,000,000 miles, 5 miles, 2 miles, it's always going to do this 1 3 thing. All right. And the obvious thing to understand is that, yeah, the 1 gives it enough velocity to do 2 units of what it just did. So you get those for free. You know, and then you have your, you know, let me just put the end here instead of there. The ground here. And that this is the only unit you actually got in a unit of time. So you got 1 unit of time here, 1 unit of time for all of this, all right? But this is all you got. This is all this is the only extra you got. This is what you get in the first unit of time. This is what you get for free. I mean, that you had to pay for, that gravity created. This is the only thing gravity causes in the second unit of time. That's it. see, will this work? Yeah, that's better. Almost better. Well, just got to get a new pen. So that's all you're getting. These are the same thing. So if I just dropped one thing 1 unit of distance, this is all it's going to do, the 1 unit of distance. I get this 1 unit of gravity. It's only 1 unit, even though it went 3 times, even though it's going 9.8 and it's going to increase its velocity by another 9.8. This whole section is the same amount of time, and the only real extra distance it got, this would have happened even if I turned gravity off. This part would have happened. So this part didn't require any added force, and the only part that needed an added force to happen was this part. So this part needed the added force, this part needed the added force, but this part didn't. That would have happened if I turned gravity off right there. This would have happened anyway. This is the only thing we added. So it's only 2 units of the push, the little bits hitting, the rain being collected. If it was rain, you're only twice as wet here. You can't be 4 times as wet. You were only in the rain 2 units of time. And we're talking about a rain moving very fast. So that's it. You can't outrun the rain, is the argument. So, that's all you can be, is 2 units of wet. You're only in the rain 2 units of time. You can only be 2 units of wet. How could you have 4 units of energy? I mean, again, if I make it worse by just saying, okay, let's do it 3 seconds, and now you're saying it has 9 units of energy. It's only 3 units of wet. How can it have 9 units of energy? And again, it gets just worse and worse. You go 4 units of time, and now they're saying it has 16 units of wet. How can it have 16 units of wet? It's only got 4 hunks of wetness hit it. That's all you added, was these 4 little hunks. How could you have 16 hunks of wetness? I mean, it's so obviously... It's so obvious that it's... No matter what you're making this force out of, you have to understand that. How can that be? How can I get 2 hunks of force and say I got 4 hunks of energy? And then especially, how can I say I got 5 hunks of force and I got 25 hunks of energy? I mean, it's ridiculous. I just, like I said, I'm just so tired of having to argue this shit over and over and over. You're just like, can't I get anybody to reasonably respond? So the only good news was, what's this channel called? Yeah, I'll probably have to look it up. You have to look up stuff when you get old. Anyway, Bruce Yearney I did email him. And, yeah, he was substitute teaching, and he did have some health things and something else, blah, blah, blah. He gave me a nice reply video. He does watch my videos. And I did try to re-emphasize that, this is an important subject, and, they really need to talk about it. And it's really disappointing that they won't. Maybe I'll read the last thing I wrote to him. Let's see. So he thanked me for the video, the roasting video. Yeah. And such, and so that was very nice. And let's see, I have to find where I responded. Here it is. Okay, I said, thanks for the expansive reply, much appreciated. Your passion and dedication makes you certainly admirable from my perspective. So I am doing a little blowing smoke, but you have to do that. I don't want to badger you on this point, but I do feel the need to make it as clear as possible. Conventional physics claims that something dropped 4 units of distance collects 4 units of energy. I'm claiming there's no logic to the assertion, and a simple can of spray paint proves the point. What matters is how long you're in the spray of paint, not how much moving around you do. 1 second of gravity just gives you 4.9 meters of extra distance and just 9.8 meter per second unit of extra velocity. You can count gravity like you were counting raindrops. How wet you already are doesn't determine how more wet you're going to get in the next second. So your accrued velocity can't change your energy. Only what you're going to add can change your energy. And you're only going to add 1 unit of gravity. 1 unit, then 1 unit. Every second adds the same amount of water. So the water you got hit you in the first second is exactly the same water that hits you in the second second. It's not a different kind of water. It's not a different amount of water. How can 2 units... well, I'm talking. Okay, never mind. So I said 2 units of time, 2 units of wetness. The fact that you might have moved 4 units of distance is irrelevant. Anyway, thanks for the reply. I'll try not to be too much of a bother and hope you likewise had a pleasant holiday. So, So at least he doesn't take it personally, which is, showing he's a grown-up. So that part's good. So the other guy was... what's it called? I don't know. It's just annoying that I can't remember names. Yeah, that's really annoying. Let's see. I never said we didn't have. I don't know who that was to. Yeah, I never said that, bitch. HB. Who the hell is that for? I don't know. Oh, there it is. Right. Okay. So see if I can't get his name off his email. Yes, that didn't help me much. Applied science. There. Okay, I remembered it. Yay for me. So so I did contact him. He basically said, I didn't block you and something. So I just contacted him, says, I guess I'm blocked, and I did try to post a video response. So I did respond to him, says, Ben, thank you very much for the reply. I've tried to contact you several times over the past few years and never received any feedback. Sorry for assuming the worst. I'm not requiring you to believe I have any credible arguments to make, but the fact is I do believe I do. I know you're incredibly busy, but if you have a moment and are feeling curious, I would appreciate you looking over this playlist of relatively short videos. So I gave him the playlist of the 13 videos, blah, 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 blah. Anyway, so, I mean, it's some hope. We'll see if he can pay attention long enough to recognize there's a subject here, and they should deal with it. We'll see. Alright, let's see if we got anything else. Let's see. Like, it's just too much for people to emulate in their heads. The physics woo is more appealing because it requires less. I know, but that still doesn't get to... It's like, look, the Valerie Rousseau guy said in his... his is the only comment on his video. And he basically says, it's so intuitive. What's intuitive about twice the velocity being 4 times the energy? I just don't understand how they can say those words. Isn't it anti-intuitive? I mean, if I say 3 times the velocity is 9 times the work, I mean, am I saying something intuitive? That's your default perception? That's somehow pushing something twice as fast is 4 times the work? When you basically are thinking, no, if it's half the mass and I push it twice as fast, that's the same work. And if it's, the same mass and I'm going to push it twice as fast, I have to double my effort. I don't have to quadruple my effort. Alright, good news is rare to come by. Yeah, well, that's, thanks. Yeah, you're depressing me. But it's just, I just didn't think this would be the hard part. I really just didn't think showing people this argument would be the part that would be impossible. That I thought inventing, the arguments would be the hard part. And that the easy part would be, once they hear it, they'll say, yeah, oh, that's brilliant. I mean, the whole thing of, diagramming charge in those 2 plus 2 plus 3, 2 kinds of force, 2 kinds of matter, 3 interactions, and I've explained electrons and protons, how they function. Perfectly. Completely. You really don't need anything else added. It's such a complete explanation. I mean, even the jiggling part, of why they don't just fly together. I mean, it's a brilliant explanation in terms of the simplicity. I mean, it's so perfectly Occam's razor. I mean, it's, yeah, okay, you don't want to believe it for some reason, but it's not going to be a good reason. I mean, there's no good reason to say, well, that's a shitty explanation when it does something nobody's done. I mean, nobody has a model explaining why electrons and protons behave the way they do. No one. There's no model anywhere. Is there? Can somebody give me a model? Is there a model somewhere? There's no model anywhere. So, I mean, I've done something no one's done before, plus I've done it so simple that, oh, fuck, how did a computer not figure this out already? I mean, it's hard for me to even imagine how AI could exist and not fall on this answer. Like, they simply ask it the question, what's the simplest way to create repulsion and attraction by these rules between two objects? We have an object that's red and an object that's blue. How do I make the red and blue objects attract each other, and I make the blue objects hate each other and the red objects hate each other? And you're saying, how can a computer not figure this out just by randomly creating different rules? It's so simple. The fact that I figured it out means it's so fucking simple, right? An idiot figured it out. It can't, it's so simple. And then you present that to people, and they just out of hand reject. No, I'm not going to pay any attention. I'm not going to say anything. I'm not going to just no comment, just crickets. And you're just saying, how can you get crickets for that? It just doesn't make any sense. I mean, it just proves that these people are just about personalities. They don't like my personality, which I don't understand either, frankly. I think I'm incredibly charming. I'm kind of funny. I'm self-deprecating. I got a lot of things. I'm not completely controlled and anal and any of that shit. I'm free with my conversation. I'm not running ads. I'm not selling products. And yet I'm hateable. Well, I know, but string theory, yes, there's nothing in string theory that's even close to coherent, right? As soon as you're creating some dimension where everything happens, some other dimension, well, it goes into the other dimension, all kinds of things happen, and it comes back with a smiley face. And everything's fine. I mean, it's not an answer, right? So it's like saying the electron goes into the other dimension, and then when it comes back, it's somehow lonely, and it runs into the other, the electron. Let's see, there is something really wrong with the idea that 2 velocity requires 4 times the work, or that it produces 4 times the work. Again, it's still 3 times the velocity is 9 times the work. I mean, come on. Isn't that on its face ridiculous? Well, I don't know how people could be afraid of somebody who finds the world ugly and disturbing. I don't know how anybody could be actually, everything is going so splendidly. I mean, how could you really think everything is going so splendidly? I'm just saying, as a psychological experiment, it's, I'd say there's something, maybe it's just YouTube. It's just YouTube has, censored my capacity, restrained my ability to interact with the world. And so I just have, marginal contact with people that end up here for dopey reasons. And so, it's just not a good test. Let's see, lots of maladaptive coping mechanisms people employ. The level to which people can delude themselves because they can't deal with the pain is incredible. Yeah, I know, but this is, I guess the argument is, we know this is more about just ego, right? So all the people who are scientist types, I'm hurting their ego. See, I'm challenging them in the sense that I'm basically saying you were in fact a dupe. You were a sucker. You were sold a lemon. So the little car they're really proud of, that they're waxing every day, I'm proving that their car is, way overvalued and it's really a piece of shit. And they'll never be able to resell it if my arguments are made valid. Their car loses all resale value. Their diploma doesn't mean anything anymore. That kind of thing. They can't be in their elite club anymore because I've proved they didn't win the game. I have the video of their star baseball player corking his bat. And so they're going to lose all their World Series rings. And they're all going to be embarrassed that they've cheated and that they weren't doing the right thing. And they weren't. It's like even Bruce Yearney, as nice a guy as he is, he's basically molesting kids' brains. He's breaking them. He's breaking their capacity to understand reality appropriately with this, revering a nonsense, silly pile of mush that physics preaches. And it goes very deep. Like I said, it's not just kinetic energy. It's the double slit experiments, entanglement, superposition. All of these things are nonsense all the way to relativity. It's all crap. So I guess that's what the problem is. People who don't have an ego problem with me being right, okay, I'm not challenging. I'm not saying to them, you're dumb, because you didn't think of this. Because they're not physicists. So they're not supposed to think of it. So they don't feel a threat from me. But the physicists feel a huge threat. Because if I'm right, they are in fact wrong, stupid, doopy, and in a sense they've been evil. Because they've been defending a fable. So I guess that's the real problem. I mean, Bruce Yearney doesn't want to admit to himself, I've been teaching kids wrong. No, he doesn't want to say that to himself. He doesn't want to write that on his tombstone. I gave them bad advice, that kind of thing. You don't want to be told you gave somebody bad advice. You hurt them. You broke them. You interfered with their capacity to understand by, believing some sort of crap that just got in the way. Yeah, I'm going to have to start making some more double slit videos because it's just huge that they've turned something so simple, it's so obvious, the slits, into all this wooey shit. I wish Newton would have said more about fringes. He did a lot of fringe experiments. But he just documented what happens. He didn't document why it happens. And, that why question is just so big. But it's just so obvious that you can just understand the aperture argument. Obviously if I make it smaller and smaller, the odds of a photon having to interact with the surface go way, way up. And it's exactly what you see happening. You want lots of fringes, make a small aperture, because then all of the photons have to interact with the surface. It's just a scattering argument. And it's just so, in hindsight, it's so obvious. I did struggle for years trying to diagram it and try to figure out how else can you explain it? How do you blah, blah. And it's just so obvious that I just didn't think of the idea that photons are breakable, and remakeable, that they're so simple, they're just a frequency. So you can take the frequency, you can break it, you can pull one of the elements out, now it's not the same Morse code. And then, I could just shove a new piece in over there, and all of a sudden it's back to being a Morse code again. It's just so obvious that that you can break the pattern and fix the pattern. And when the pattern's so simple as on and off, bit, no bit, obviously you can say, well, I could just take random bits, and if there's only a 50-50 chance, I mean, if it can't be all the way out of phase or all the way in phase, doesn't matter. It just matters that you're on one side or the other. You're either going in phase, you're a photon. You're going out of phase, the second half of that, you're not a photon. So, I mean, there's no other choices. They're either going into phase, you're getting close to being in phase, or you're the furthest away from being in phase. Those are the only two things you can be. And, with that simple argument, you can just say it was 50-50. Yeah, I just throw random shit at the wall. There's a 50-50 chance I make a photon. The catch is it has to be the right polarization, and you have all these other rules. I mean, the funny thing is that photons, it might not be about the frequency. When we detect a color, it might not be the frequency we're detecting. We're detecting the polarization, because the polarization is proportional to the frequency. So we really might be just measuring polarization and thinking we're measuring frequency. Alright. It'd be great to be able to simulate double slit experiment. Yeah, so I have a guy that can do that, was doing that, and then, stuff happened in his life. And so he needs a little break, but hopefully he'll come back to making those simulations, because there's a few of them I'd like to just simulate gravity, frankly. Just as particles, because it's not a very difficult experiment to simulate. Yeah, I wish I was also willing, to learn. I have tried. It's just, I'm just, it's the old dog problem. And so much time, I don't learn that quickly. So it's like I have to fiddle with something a few times. And I guess it's the language of the programming too. I don't like it. I'm a cut and paster. I don't. All my code is always written as the variables are always XW2. They're never literal variables describing what actually is in the variable. And so I have so many bad coding habits that I'm just very bad at it. But it's also, you have to sort of, when you start getting a program that's controlling 10,000 little bits, it's hard for my brain to understand how the computer is actually doing that. I mean, how does it buffer its own capacity to know where each one of those are and all of that crap? So you're almost like saying, well, isn't there some point where you're going to end up with a buffering problem, where the reality you're showing is way behind the calculations you're making? And so my brain just can't get exactly how computers handle dealing with 10,000 individual items. And so that's a little bit hard for my matrix kind of math. It's not my thing. I never liked variables that had like 490 different things in it. That were a label for, there was somehow the same variable has 400 elements, and then you're trying to control each element. And anyway, it does get complicated. Even the guys who know what they're doing, the subtle problem that existed in the current simulation, like some of the older versions of the simulator for charge worked better than the new version. And it's mostly because of how do you create that perfectly random external universe? Because you can't have the force bit that acts inside can't have anything to do with how many are coming in from the external universe. So whatever happens inside the simulator can't affect the source bits. And so the computer is actually reusing the bits. And that's where you get into a problem, because the bit leaves the simulation and then it doesn't come back perfectly randomized. And so that was sort of the problem, is that, I wasn't getting enough of a... And so the fix is kind of simple, is that every time a bit comes in, an opposite bit comes in from the other side. So once that's fixed, it'll fix, because it'll give it some sort of equal pressure in all directions all the time. And that's what it's missing, because it's very hard to simulate a whole universe. But anyway, that's what I'm waiting on. So that should get done this month. And then once that's fixed, I think we're going to just make the code public and see if somebody else can do the rest of the building of atoms and, the rest of the three-dimensional crap, if any. I mean, 3 dimensions are going to be really a bitch. But anyway, maybe somebody will be willing to do it. But, I'm very, these people are working for free. They're doing it, as a nice gesture. It's, I can't, it's just, I'm very grateful for their assistance in this project. You can't, and it's so helpful in a way once you see it, I mean, once you see it happening, you're saying, yes, it really does work, and it gives you more tools for your own imagination, and, that's very helpful too. Probably without the simulation, I would have never realized about all the noise, and how the noise deters the simplicity of the argument, right? I can say 2 + 2 + 3, but that doesn't say that, the real universe is this, and that noise has to be recognized as an inhibiting factor to any of that alignment thing where they're just bang right into each other. They can't just bang right into each other. I mean, it sort of explains why you need the high pressure of suns to create nucleuses. And that's another part I want to go over, is the fusion thing, because that subject really does bug me. The idea that they're trying to argue that you can make energy by, compressing, pressurizing some form of hydrogen, right? But they're not even using hydrogen. They're using deuterium or tritium or some more complex elemental. I mean, it's not simple hydrogen. And so, they're cheating, because, you can make arguments about, the end product, but it's just kind of, I mean, the helium nucleus is this interesting, the idea of the 4 protons and the 2 electrons, because you could argue, okay, I can understand how to do it with 1 electron. There, I did it. I made helium. But the trick is there's the 2 electrons are on either side. So if you have to really think of the helium protons as being in a line with each other, okay, so they're like that. They're on the same plane, and the electrons are here and here. And so that's helium nucleus. And, that's what makes it interesting in terms of clearly a very polarized object. I mean, you could say north side here, south side, so it's a magnet in 2 dimensions, And what else does that mean? So obviously the electrons, for the the helium atom, the only place they can be is out here somewhere. You would argue. Because it's clearly a very accessible protons. I guess it's well, anyway, it takes some thought to figure that out. I mean, it's the geometry thing. There's lots of ways for you to draw that geometry, that 4-to-2 geometry of a helium nucleus. And then figuring out, where to place the extra electrons. But anyway, so even, that could take some real time to do. But anyway, that's, it's still made out of the same principle of the fact that the electrons can't, they can see each other, so they're repelling. But they're very attracted because there's 4 protons for them to be attracted to. So that's the game being played. See how many viewers we have. Seems the same people all the time. That's the problem. Just not getting any exposure out of YouTube. It's funny how every now and then one of my videos gets 300 or 400 views, and you're just, out of nowhere for no good reason. It's just so annoying. It's just like, why? Why that video? What was special about that one? And there's no way to figure out what was special about that one. Well, anyway, back to the fission thing. Yeah, it just doesn't make much sense. And my basic argument is the sun is hot because it's gigantic, and it's a gigantic pressure in the center of the sun. And so, I mean, you're just talking about an awful lot of electrons and protons doing this kind of crap. So there's a ton of energy stored, because every time they're moving, that means a Sisyphus has to be pushing them. So you have all of those elemental bits doing all of that jiggling. And you're saying, why wouldn't gravity be enough right there then? Why can't you just say, okay, there's no heavy elements to get in the way of the heat getting out, right? So for the Earth, you're saying, okay, you have 5,000 degrees in the center of the Earth, okay? So it's 5,000 degrees in the center. But as you go out, right, it's more and more mass, so it gets colder and colder and colder until you get to the surface, and it's not anything near that, right? So if the sun wasn't shining, the surface of the Earth would be like minus 300 degrees Celsius or something. Really cold. But that's only because you have to think in terms of real temperature, Kelvin kind of scale. And so even by Kelvin scale, you're still, 100 degrees or something like that. I don't know exactly what the numbers would be for those numbers. I think 300 Celsius minus 300 would be like 50 Kelvin, but whatever. But, the sun is, a million times the size, and I don't know, what is it, 100,000 times the mass? I don't know how much more mass it has. But anyway, it's a ton of electrons and protons. And so it's an awful lot of energy that's been absorbed. That's why the gravity can hold the Earth in orbit. It's because of the energy absorbed. And the photons, it really is a reflection of temperature, right? So so you're saying it's small atoms, a bunch of hydrogen, so they can jiggle very quickly. Where the heavy, stuff that we got a bunch of iron on the surface and aluminum and all kinds of heavy metals on the surface, and so all of that stuff can't jiggle very fast. So the trick is it can't boost the reflected energy. The energy coming in can't be reflected out, okay, at visible light kind of frequencies. But because the sun is all light elements, and they're moving with more energy because the sun's bigger, they're moving much quicker. So when they push out, they compress infrared photons into visible photons. So they can create higher frequency photons. So we see the sun as being hot. But it's not really hotter, okay? By total, energy, it's hotter, but it's not it's not, visually it looks so much different. But that's just the visual part because of the fact that the surface is hydrogen. And if the surface was something crustier and heavier, then it wouldn't look as hot. I guess it's a simple way of saying it, but it's more complicated than that. But I think it's just gravity, so I don't think there's any fusion argument to be made. It's not fusion that's fueling the sun. Gravity's fueling the sun. And what gravity's doing is making neutrons. It's taking electrons and protons, putting them very close together, and then making nucleuses out of that. I mean, it's taking the elemental dipole, a neutron, and putting it together into nuclei. And instead of calling it what it is, neutrons, we decide to say, well, there's 2 neutrons and then there's 3 extra protons. But there really isn't. Okay, there's just electrons and protons. Well, anyway. The difference between the neutron, okay, and the simple truth is that, there's my neutron. Well, the simple truth is, yeah, I can add an extra proton. Okay, now which one of these is the neutron? Is this the neutron or is this the neutron? You see what I mean? It's not once it's in a nucleus, you can't tell the neutrons from the protons. It's all the same. It's just electrons and protons. You're just saying there's twice as many in the nucleus. There's always twice as many protons as there are electrons, in most cases. Obviously, in the heavy elements, it doesn't make any difference anymore. So it's not a 2-to-1 relationship anymore. But that's the basic theory, right? Is that you're just saying you can add, the isotopes. You're just adding an extra proton or taking an extra proton out. You're just changing that ratio. But it's really just electrons and protons, and you're just arbitrarily making some declaration that a certain number of them are neutrons and a certain number of them are free protons. But you could just make the argument that, yes, the number of electrons tells you how many pairs you can make, but if you understood it as being triplets, deuterons, okay, then you could just count them as these things instead. Because this proportion will always be. You're always going to have 2 protons and 1 electron. So you're just combining those things to make nucleuses. You're just adding this, a neutron and a proton. Yeah. So I think that's a good enough argument. Yeah, I think so. Yeah, because a helium nucleus is, it's like it's more than 2 hydrogens. I mean, it's 4 hydrogens if you look at it, in a way. So, it's obviously more than just one of these. I mean, the hydrogen is this, and then you're just, it's all made out of the hydrogen, you could argue. Hydrogen is a neutron. So hydrogen free, the electron and proton are farther away because of all the jiggling. And when you put them inside of a nucleus, they get close enough together to be called a neutron. And that's really the distinction. Yeah, I think that's a reasonable way to say it. But even that, I mean, this is another simple argument. I mean, all the physicists say it. I mean, they concede the point. They say neutrons decay into an electron and a proton. They say it, and an antineutrino. Let's just forget the antineutrino. How can they not concede? Well, then why are we calling it a neutron, right? Because it's not really a particle. It's obviously a composite object. And then you simply put the other proton on the other side and you say, well, there's the strong force. What do I need a strong force for? I mean, Maxwell's drawings clearly tell you, right? I mean, how could people not even do that? I mean, you have Maxwell's drawings telling you that electrons and protons really love each other, and they're going to try to smash into each other whenever possible. And you can understand that, well, if I have a proton and then I have an electron and then I have another proton, obviously that unit would get two protons really close to each other. I don't need a strong force to get protons close to each other. And it's only because they originally thought of the neutron as being some kind of weird proton-y thing that had a neutral charge. It's only because they thought of it as a neutral charge that they broke the continuity. Because if they thought of it as a dipole that actually did have an electron, and that's what, what's his face actually believed. Rutherford? Yeah, I think Rutherford actually believed that nucleuses had electrons in them. And, and it was Bohr who ruined it all, by claiming the neutron is a neutral particle rather than an electron and a proton. So, I mean, even there, this physics was forced. It wasn't intuitive or natural because the people who invented this stuff didn't even believe it. It's like the guy who discovered redshift didn't believe space was expanding, and thought the redshift was being caused by some physical phenomenon, and yet that got destroyed as an idea, and we all had to accept that somehow space is poofing into existence. Just so bad. Let's see. I want so badly to believe fusion reactors will one day be viable, but it's always 10 years away. And it's such a lie anyway, though. You have to really recognize that, this very idea that you can somehow initiate a plasma that just continues to plasma, that it's just going to, that they actually are going to create some kind of ball that's actually just going to keep producing heat. And they're going to be able to control that thing. I mean, it just... And then when you see the reality of it, I mean, the fact is this thing's going to create all these high-energy neutrons. It's going to deteriorate the materials that are contained. The container's going to get ruined every 3 days. It's going to be radioactive waste for 100 years. It's just, And you have to put so much energy into it to light this thing, to initiate its function. And there's just no evidence that they have any mechanical system that can really contain this plasma. That can maintain the pressure even. I mean, the amount of energy you have to put into the magnets to actually force the whole thing to stay compressed, it's almost like the gravity argument. You're going to end up using so much energy to compress the fucking thing that you're not going to get all of this free energy you're hoping for, because you're having to put so much energy to contain the fucking thing that's making your energy. Frankly, I don't even understand how they can think it's going to work at all, because I can't even understand how the lifetime of the magnets would be very long. I mean, you can't really shield them. They're going to get, the shit kicked out of them. So I can't even understand how they think that's going to work. But I don't even think it, like I said, I don't even think it's correct. I don't think there's any other way to extract energy, stored energy from atoms or nucleuses except by breaking them. I mean, the idea of making them creating energy just doesn't make much sense to me. You have to break them. You have to break something that has energy. You can't take things that don't have energy and make them have energy, because all those things have to be given momentum. And maybe it's just because of this might be another thing created by 1/2 mv squared. That they've completely miscalculated, because they've assumed when they have the little particles going at the higher velocity that they actually have more energy. So that might be, it might be that simple. I didn't think it. That's why fusion works for them, is because they're doing the math based on this idea that when it's a clump, that somehow it has less energy than when you break it into little pieces and give all the little pieces their equal momentum. So if I take the recoil of the gun and I convert that into a bullet, they have this exaggerated notion that now the bullet has 1,000 times more energy than the recoiling gun that created it, if you get my drift. So that's why they think fusion works, is because of the stupid 1/2 mv squared. It's fucked up the game again. It's the reason why they think this makes sense, is because by kinetic energy, you're increasing the amount of energy by making small things move fast. And you can't do that. Yeah. Oh, yeah, that's probably it. So I have to go find some math on, fusion, and see if I can catch that that's all they're really talking about, is they're miscalculating the energy. Because they did that to the mass of the electron. We really don't know the mass of the electron because they calculated the mass of the electron using 1/2 mv squared, and they got the wrong answer. They got an answer that's way under the real mass of the electron because they assumed much more energy was in the velocity than was in the mass. And so the very high energy they had to make, they had to increase the velocity, and they had to reduce the mass. So the electron had to have a lower mass to be able to fit the kinetic energy model. And if you did it with momentum, then the velocity and the mass were equal sharers, then the mass ends up being much bigger. I have Gary's live stream playing on 5 devices on full volume. Well, that sounds a little bit like you're crazy. I mean, you could just say, I'm crazy. You don't have to give us the exact description of your craziness. But I do have devices. I have to admit, I have a lot of devices that are... I got a broken, these cracked tablets. I just, sometimes you find some kind of deal that's just, so they're all cracked, but they work. Yeah. And I was able to upgrade them to Android 10, which is, pretty functional. So I can run my cameras and different things, and it's very low wattage, and so it's quite efficient. And you barely see the cracks. Cracked screen isn't that big a deal. I have like a little screen over there that was just for photo slides, that was supposed to just display photo slides, and you can play videos on it. And so I got those like 10 years ago, 15 years ago. And yeah, they all had some kind of bug. They didn't work perfectly, but I got them working well enough. But I mean, it's lasted for that long, and it plays 24 hours a day. It's got like 25 movies on it. And I just, every now and then I can just look over and see some kind of clip from a movie, and it's, does keep my brain from going crazy. But it's funny how that's really old technology. And yeah, it's not high resolution, all that kind of stuff, but it's not bad. It's, 640 by 480 kind of resolution, but it's, 12 inches, so it's pretty big. It's not bad. But it's funny because it almost plays video better than the Androids do. You know. But you do have to put everything into old video formats and blah blah blah, so that's the hassle part. MPG files. And the right version of MPG file and all that stuff, whatever. But anyway, it is surprising how it really has been a fixture of my existence for a long time. Yeah. I used to have, like, you know, where I used to live, when I had my old, whatever, man cave. You know, I had like 4 of them. So it just, you know, no matter where I went, there was something going on. I guess it's a way just to make living alone more palatable. But I really, you know, I don't like people much. I don't like company. So it's good to have some kind of synthetic thing. Some non-human thing. I don't know what that means, 500 cigarettes. I don't know what that means. Just no idea. I haven't had a real cigarette in, like, I don't know, it's over a year now, I guess. Long time. I'm running out of nicotine juice, so I really have to decide whether to buy more or try to quit. Really would be nice not to be addicted anymore, but I just can't imagine my brain without my nicotine. Can't imagine it. Can't imagine it in some good way. Yeah, that's it. It just seems like a horror story. I probably should put the chat in the thing and just get ready to go. Yeah, so I'll put the chat in there just when I'm ready to go. Let's see, where the hell is it? Where is the place for doing that? I guess I could do it here. Doesn't matter. Firefox, I guess that's it. I turn it on. And there it is. Alright, so let's see if somebody can say something interesting. There's 8 of you now, I guess. 8? Is that what it says? 8? Can't quite see the number. Yeah, 8. All I have to do is pull that over there a little bit and then I could see it. Yeah, now I can see both. Alright, that's better. Not that it matters much. Oh, let's see what else. So that's the thing too, you know, I was just thinking about hydrogen again because I was thinking about fusion again, and you know, they don't even describe hydrogen accurately. You know, because people just say hydrogen. And so I've thought for most of my life that hydrogen just meant, you know, an electron and a proton. And it really doesn't. And, you know, that's... So the common hydrogen, the hydrogen that's 99% of the hydrogen you interact with, isn't hydrogen. It's this. It's hydrogen 2. Okay? And this, you can say, oh, well, that looks so damn stable, right? Oh, you can't see it now. That's hilarious. Ha ha. Yeah, you screwed yourself there, Gary. And what do I have to do? Yeah, I just get rid of that for a second. Alright. So this is hydrogen 2. You could understand that it has to be something like that, right? There's just so obvious. You have an electron and a proton as hydrogen. You'd have to understand that they were going to end up creating something that would be electron, proton, you know. And that's what hydrogen really is. It's not, you know. And so that's a lot different, right? Because that does look like 2 neutrons, doesn't it? Yeah. And that, you can understand that if you're going to use that to make helium, that makes a hell of a lot more sense, you know, except that you have equal number of electrons and protons. But you could just understand that you could take a piece of this hydrogen and a piece of, or I guess you would take this piece, right? So if you were to make a helium nucleus out of 2 hydrogens, that is 2 hydrogen 2s, you know, you would take this, okay, and another one of those, right? And then you'd end up with your 2 electrons and 2 protons. So you do, you know, this kind of thing, you know, this and this. Those 2 combined would be helium. And the idea is what did you lose when you did that? You lost 2 electrons, right? I mean, I guess I should draw them this way. Right, so you lost 1 electron from this one, and you lost 1 electron from this one, so you lost 2 electrons. So you can understand that 2 electrons could have some energy. But the idea is they're thinking these electrons have an exorbitant amount of energy because of their velocity. So because they're squaring the velocity, they think this is really hot. And it's really not. Yeah, so that's the catch. They've over-exaggerated how much energy they're getting out of the reaction. Because what they're saying is let me bang the force in a big clump, okay, you know, a heavy MV, and they're going to convert the heavy MV clump into this tiny M and big giant V. And then they're going to, because they're squaring this big V and squaring this little one here, they got this huge energy differential between what they put in and what they put out. And so that's the flaw in their math, is not recognizing that this is the same energy in as the same energy out. So they're never going to get what they think they're going to get. Let's see, say something interesting quick. Yes, and you're not doing it. Or you will be forced to watch 100 hours of Vsauce videos. Well, whatever. I have to go find his channel, I guess, his old channel, and see if he's made anything interesting. But yeah, I found all his videos to be really obtuse, frankly. It's like most of Veritasium's videos, you can't even respond to them because they're just not even about a regular subject. Not a physics subject, anyway. And he doesn't even make the video. I mean, now it's, you know, it's just so overproduced. He's got all these other foreigners who are chiming in with their bullshit. Ugh, it's just really annoying. And that's science on YouTube. Terrible. It is funny how people become so popular, you know, and the old ones, you know, because you're just saying, yeah, what was it about this Vsauce guy that was so interesting? I just don't get it. But he made, you know, in a sense, he made Veritasium. I mean, Veritasium got famous through Vsauce. But anyway, no point in me lamenting about it. I don't know what the magic is, and It's just the videos that appeal to me are, like I said, real people talking in terms of, give me a real answer and show me how it works. And then there's none of that in all these physics videos. So I was watching hydraulic videos today, and they keep trying to make everything into a kinetic energy thing. So they just end up saying, first they explain it as momentum and say, well, it's all conserved, and then they do this kinetic energy thing. And you're just saying, how can you make both things work out? Because they can't both work out. And then you have to find the catch, where they say something like, the flow rate is the same. And then I'm saying, well, how can the flow rate be the same? Okay, I have a pipe, and it narrows to half the volume. All right, now, yes, it's half the volume, but the little bits are going to end up coming out at twice the velocity. So they'll explain it and say, look, it's all, it makes sense. And then they start squaring this, and you're saying, well, how can you do that? Because now you're saying there's twice the energy here, and all I did was, how can I make this same pressure be twice the energy? And then they say the pressure goes down here. That this is a low pressure, and you're saying, well, how could it be a low pressure? Because frankly, that's a stopping point. I'm increasing the pressure. If I have this thing wide open, it's got to be low pressure, because now I've allowed everything to just move, and I'm not constraining it. I'm not forcing it to change anything. I'm not doing this. I'm not forcing things to smash into the smaller space. And and they base it on the Archimedes principles and such. But I just mean and whatever the other guy is, the B name guy. God, I just hate this getting old thing. Where the idea is that you have a tube with fluid in it, okay, and if you run air across it, it'll pull, okay, atoms out of the tube, because theoretically, because I've increased the velocity here, I've lowered the pressure. But does that really make sense? Yeah, I mean, is this the high pressure? Do I have to have and then I go low pressure here? I mean, what point do I have to have the low pressure? And all I really have to do is have air go across here. That's all I have to do. And it's going to drag molecules out, because they can't go back in, so they're going to get dragged out. They're going to get pulled out. So it's not technically low pressure, you would argue. I mean, it's going to behave like it's a low pressure, but it's not technically low pressure, is it? It's just that you're taking the atoms away. So they're not pushing on each other anymore, They're moving away, so they're not pushing on each other. They're not weight on each other anymore. All the weight of these atoms in this thing, all of their weight isn't on top of each other, because the top ones aren't putting any weight on because they're getting blown away. Yeah, it still doesn't make any sense. So I don't think there's technically a really low pressure. They're just saying because it rises, that means it must be moving from high pressure to low pressure. But it's not really. That's not really why it's rising. It's rising because you're pushing the mass out. You're getting rid of matter. Anyway, he doesn't really make videos like he used to, though, at least not in the same quality. But they're still nice to watch every once in a while. Okay, well, he says you. I just wonder what subjects there are. I mean, that's the other problem. Nobody makes these videos on these elemental subjects except to do the math. It's like look, it's like that stupid Valerie Rousseau guy, right? He makes a video where he just does a bunch of math equations saying, look, I can do math and I can predict an outcome, and I can predict it in my head. In the sense that I was really just saying, well, you tell me, how much did you really drop? I mean, that was the trick he did, in his video, was just so annoying. So I already gave him the chart where I, obviously my predictions. And I predicted that if, and this completely is confirmed by physics. It's not like this is established by any other rule than physics itself and experiments that have been done. So, you know, you drop something 1 centimeter, and its velocity is going to be, you know, 1 centimeter drop in gravity is going to equal 0.44 meters per second of velocity. So you know that if you put a ramp, that's what you're going to get from 1 centimeter height. But the trick was, he raised it 1.5 centimeters. Okay, let me do that this way, 1.5. But the point was, he was only rolling the object from here to here. Okay, so it wasn't a 1.5 drop. It was only a 0.25 drop. And so when he got the answer of 0.25 or something, it's only because, yeah, he didn't drop it a full centimeter. It wasn't even dropped a full centimeter and a half. So he never dropped it a full centimeter and a half. He only dropped it this amount on the ramp. But I could have predicted the outcome as soon as he said, look, if all he told me was that it's a 1 centimeter drop from the point I'm going to stop the car and the point I'm going to allow it to fall from, and it's a 1 centimeter height difference, then I could have given the answer without even doing any equations at all, because I already know it. I already know what 1 centimeter creates, so it's 0.44 meters per second. So I didn't have to do any math at all, because I already know the number. 2 centimeters is going to be 0.8884 or whatever. You know, it's just going to keep. Well, no, it's not. I don't want to start messing with the velocity parts because that changes. But it's going to be 4 centimeters is going to be 0.88, right? Twice the velocity, yeah. So I have those two numbers already in my head. So I don't, you know, it's pretty easy to do the calculation. If you give me some other number, I can just do the approximation and come up with a pretty close number. So anyway, it's just, but it doesn't, you know, again, nobody disagrees that 4 times the height is twice the velocity. And he's basically saying, well, because I proved that 4 times the height is twice the velocity, therefore I proved that twice the velocity is 4 times the energy. And it's just like, no, you didn't. I just know how he got away with it, how he thought that was a real argument. That somehow he's proving it takes 25 times the force to move something 5 times as fast by doing a few mathematical calculations that everybody already knows because everybody knows what Galileo already proved. You know, too stupid. My things are creepy was a fun one. Okay, well that sounds reasonable enough. He's creepy. But why would you have 5 kids in a creepy world? That's creepy. Well, whatever. Obviously it's one of these personality things or whatever, but he just, I don't like him. Don't like his style, don't like his look, don't like anything about him. Don't like fucking 5-minute cancer commercials in the middle of a video. I really don't like that. Ugh. You know, when non-profit companies are doing commercials, they're just saying, gee, you know, that doesn't make much sense. Yeah, well, I don't know, and it's all kind of garbage. Look, he did the video I responded to. I didn't think it was going to be on the Drake equation. But he basically conceded at the end of the video that, okay, I'm conceding, there's no aliens. And so why have the conversation in the context of somehow pretending that you haven't already drawn a conclusion? I mean, it just seems kind of ridiculous to not just give people the best of your impression that, yes, if there were any advanced civilizations, they would be making enough noise for us to hear them. And we don't hear them, so they really must not be there. I mean, the law of averages, it's just you're basically saying, look, there's a bunch of plants that just formed today, and it'll take 5 billion years for them to get anywhere, you could argue, if they were going to get anywhere. So we certainly can't talk to them, but, the ones that started 10 billion years before us, yeah, they should be way ahead of us. Yeah, I don't know what you're saying. I mean, everything you're saying is a little bit obtuse. It's essentially child's play. I don't know what that means. Okay, but it's childish. Let's just say that. Okay, I get that. It's just a bunch of whimsical pretending. I sort of thought of that today when I was making my other video for the other channel, because I was just thinking of like how terrible it would be to get killed by Martians. If Martians attacked and I got killed by Martians, what, getting killed by cancer is somehow worse? It's just kind of almost laughable. You say, why the fuck would I be afraid of this other thing when the thing that's already heading for me is about as bad as you can get, right? I mean, the natural death is pretty horrific. And you're saying, well, why should I be afraid of anything else except the timing problem, right? It's going to happen when I don't want it to. Well, that's going to happen too, no matter what. So it's like you're so fucked. And it's like we're just, like I said, everybody would be panicking if it was the Martians. They're going to kill me and I don't want to be killed. Well, guess what? When the real thing shows up, you're going to be saying the same goddamn words. It's going to kill me and I don't want to be killed. Yeah, it's just funny how people's reactions are just so backwards. So it's the whole thing, like the drunk drivers kill people every day. No one gives a damn. No one throws flowers off of bridges or anything. But you die in a spectacular plane crash, oh, they'll remember you forever. You're the most tragically affected humans on Earth. And the person died that fast. And it's, you're just saying, yes, it's just such bullshit. So are space elevators. Well, yeah, I mean, there's no real viable physics for that kind of shit, I don't think. So, with just the matter itself weighs way too much, so you have to have some special new matter. But, yeah, there's no physics that make it possible. No current, real physics. But that's like anti-gravity, that's like warp drive. There's no rational physics. There's no way you're going ever faster than the speed of light. It just can't happen, ain't gonna happen, not gonna happen, ain't gonna happen. How many times you can say it, but it just ain't gonna happen. And even if you could make it happen, there's no way it could happen because every particle, every hydrogen atom you hit in space will blow your ship up. So there's no point. You can't. There's no way to make it viable as a mechanism. You'd have to remove all of the matter in your path, So for billions of light years of matter, that's really there, you'd have to somehow scoot it all out of the way. You can't even imagine how much energy that would take. O'Neill cylinders are childish, and these scientific fantasies show the goofiness of this world. Yes, well, it's true that this is what people waste time imagining. I mean, they really have ruined sci-fi, right? Because, this whole time travel thing, you just can't play with that and have a rational story. I guess I can't say that entirely. I mean, obviously they're good stories, but they're good stories like some voodoo story or some horror film that has witches in it or something. I mean, maybe it's watchable, but it's such terrible science. They need to make more probe episodes, like Star Trek, where you would bump into some programmed probe or something that has an agenda and you have to fight with the computer. Those are, to me, those are realistic things we can run into, where our own AI satellite or something decides, something, does a howl, howl the computer. Yeah, those are kind of good things because that's just interesting to have those logic arguments. And trying to find some way to defeat the system, to steal its energy source or do something, so you can make a story out of that kind of crap. But, sci-fi with aliens just doesn't work because, they wouldn't bother coming here. Let's see, I brought this obscure book called Futurist Fantasies. Katie Van Allen. Well, that sounds like a fake name, yes, and it was really interesting. Maybe I'll send you a link to it. Okay, maybe. Yeah, it doesn't. It's not going to hurt to send me an email, I suppose. But anyway, or post a comment somewhere where you can post a link and such. Alright, well, I guess it's good enough time for me to retire and get a real job and all that kind of crap. So anyway, it's kind of a throwaway video, but yeah, just gotta find some evidence somewhere. Or I'm actually going to have to make evidence. I really don't want to do experiments. Got to find somebody to do them. That's why that applied science guy, he does very good experiments. I mean, he builds very good hardware. If I get him to pay attention to this subject, it would probably be to our benefit. It's hard to get them interested. Alright, so till it be the next time and such and so forth and whatnot, blah 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 blah. It was 50 cents. It basically demonstrates how most of the modern technologies we fantasize about, like plasma reactors. Yeah, well that's, fusion. But anyway, I didn't think they actually spent as much money as they have spent on this, and I didn't realize the government spent so much money. But that thing in Europe, $50 billion? That's a lot of fucking money. And I wonder who the fuck's going to own it once they actually did something. What's going to be the catch? We're going to have to pay gigantic royalties to some patent? That's just, the whole thing. You might as well flush it down the toilet if we have to pay for it. But anyway, we'll see. I mean, all these private companies, right? That's their investment. So they're all trying to do this so they can screw us for decades. So the free energy won't be anywhere near free. But anyway, like I said, I don't think they're ever going to get it to work. Because I think they've miscalculated how the damn thing functions. Because of 1/2 mv squared, again, it's just in the way. You want to, it's ruined physics. It really just has ruined physics. It's created all these phantom particles, all of this antimatter, all this nonsense is all a byproduct of this silly squared velocity. Ugh, just so stupid. Well, anyway, it doesn't matter. Everything's stupid. Everybody's stupid. They really have so little of life right. Just can't get the physics right, can't get the ethics right, can't get anything right. It just sucks being on this planet. Sucks having to look at it and watch it. It's all just such a tragedy. I don't know. It's like sitting on the Titanic when you know it's the Titanic. You know what's going to happen. And you just, nobody will pay any attention. But anyway, alright, so till the next time, and such and so forth and whatnot. I don't expect much from people. Most are dumber than rocks. Look at that graph science. Well, look at that. I didn't know you could do that, an at thing. Wow. He added me. Yeah. Anyway. Till next time, such and so forth and whatnot. Okay, I'm done. Just have to find the button to hit. So, good night. There. The traditional ending. Good night.